Welcome for this today webinar about extension of 3D optical profilers to wide field and rough samples. I'm Samuel Lesko. I'm leading the application development team for optical profilers, and I'm dealing with the Bruker nanosurfaces divisions. So Bruker nanosurfaces divisions deal with a wide range of surface-based technologies, going from atomic force microscopy and nano IR, so chemical analysis at nanoscales, all the way through stylus profilers, tribology and mechanical tester, such as micro indentations, scratching, or going to nano mechanical properties with nano annotations, nano scratchings, all the way through multiphoton and super resolution fluorescence. Today's webinar will focus on 3D optical microscopy. The previous webinar was about optical microscopy based on white light interferometries. So today's webinar will highlight the focus variations technologies. So today, this webinar is all about understanding how complementary focus variation technique is versus white light interferometry. And for that, you will be given elements to understand where to best use the focus variations or the white light interferometry with that respect. But also you will understand the reason behind the fact that focus variation is really suited for rough surfaces and wide field of view through its principle and illumination path. Finally, we will highlight and you will understand all the capabilities of focus variation versus a given space, application space. As you see, we have a wide range of different applications, and today's webinars will emphasize some of them, such as tribology, corrosions, aesthetic perception, as well as a new manufacturing technique. As you have already noticed, everyone is on mute, so whenever you will have questions, please use the chatter box to bring your questions along these presentations. I will answer them at the end of the session. So first of all, focus variations is a known technique, and we will check its principle in order to understand the reason behind its effectiveness versus rough and large field of views. So basically, focus variation is pretty similar in essence as the confocal technologies or white light interferometry technologies. We have, let's say, a bright field objectives at that time, which focuses light over a surface, and then the light bounces back to a camera that visualizes the intensity and colors. So in that case, the color cameras is in use, and in order to get topography, we get vertical motions during which intensity maps are all captured. In order to obtain the 3D topography, one need for every pixel to find the corresponding height for the best focus. And here, this is where the difference lies for focus variations. Focus variation is based on the principle of determining the best contrast in order to spot out the focal plane. So this could be illustrated with this intensity map images, and you can imagine that you have a single pixel surrounding by some near spot, and as you can see, whenever we're in a perfect focus, there is a strong contrast between all the different pixels, and there is also, in terms of intensity contrast as well, or color contrast, there is a clear difference versus what is out of the contrast, where the wall sharpness is lost and there's a blurring effect, as well as the contrast has been weakened out. So for every pixel, the system map out the height for which the best contrast is provided in order to obtain a topography image, as you can see on the right, together with infinite a color image, color and intensity image, because meantime that we record the height, the system also store color and intensity image all in focus. So the conclusion here is with focusization principle, we obtain two different formations, topography and color image, based on the contrast methods. So now, principle does not really uncover the reason why focus variation is made for rough samples. Actually, when we look to confocal and white light interferometry, we only use coaxial illuminations. In that essence, confocal and white light interferometry are directly linked to the reflected intensity coming from the illumination path only. And this requires a single coaxial path to make it work. So what's happened in case of very rough surfaces, the light might bounce away from the collection angle of the objectives, and there is, by essence, a correlation between slope capability and objective. The higher magnification we have, the steadier slope we can get at a certain first glance. As we saw with white light interferometry webinars, if the surface is a bit textured, we can just push back the limit and collect data up to a certain level out of this numerical aperture limit. But there is a clear bottleneck here. On contrary, focus variations is based on contrast method. So whatever light we can bring extra to reveal details and get contrast is more than welcome. So that's the reason why usually we use a ring light made of LEDs on top of coaxial light, such as the shadow angle of this light will bounce back toward the objective and be seen by the cameras. So it allows a focus variation by essence to really study a very high slope even at low magnification. So for instance, a 2.5x objective can easily measure 70-degree slope or even higher. So as we can see is by essence, focus variation with this light path of a ring allows better capture of a steady slope. But also, there's another element that make it very effective for wide field and rough surfaces is simply the scan speed. So what if you see some example of images taken on a black foam, on a USB board, or on a geared teeth, you see the volume being very large and the data being captured in fractions of minutes or less in some cases. And the reason behind this is simply that we have high vertical scan speed, and it can go up to 6 millimeters per second, making a single image on this geared tooth very fast in a couple of 5-6 seconds only. And then you can collect multiple field of view, such as you get all the information you need. So as a summary, focus variations has a proper lighting and scan speed, making it very suitable for rough surfaces and large field of views. The point is, whenever we speak about 3D optical profilings, the main idea is to be able to measure and quantify some element of the surface. It can be roughness, it can be step height, it can be width. So all that relies on the metrology capabilities. So definitively, focus variations implemented by Bruker comply to that. So here are the few evidences about key essential parameters for metrologies. So first of all, what you want with the 3D optical profiler is whatever the step height you measure, you want the answer to be right and accurate. So this is what we call absolute vertical linearity. So if you measure a step which is close to 1 millimeter or 4 millimeters, you can see you have a nice linear progression with respect to what is measured versus what is expected on a gauge block, for instance. Likewise, whenever you want to measure a certain step, you don't want the measurements to be affected by the positions along the scanner. So with the focus variation technique we have implemented at Bruker, we have almost 80 millimeter scan range. So we can measure like a 200 micrometer step whenever it's on the stage, lift by 25 millimeter or lift up by 50 millimeters, and ensure that actually the difference, differential linearity is better than 0.3%. So this means irrespectively to the position along the scanner, you will be able to measure the same step or same roughness in accurate ways. Also, because 3D optical profiler is mainly used for roughness measurements, we have checked how well this focus variation techniques comply and match with white light interferometry technique, as well as with independently certified roughness comparators. So this is a surface comparator we work with, which represent different technologies of manufacturing, such as milling, turning, grinding, lapping, with different kind of amplitude of roughness, mean roughness. And what you see is in green, what you see is the certified values. In red, this is the white line interferometry values. And then in blue, you see the focus variation technologies. That shows a pretty good agreements up to somehow 0.8 microns roughness, where it starts to deviate simply because the 20x objective start to have a too high background noise here. So there are two takeaways here. As first of all, as focus variation comply in terms of roughness application, which means, by the way, that the lateral calibration of the objective is properly set. The second one is after certain limits, the focus variation will not be applicable anymore. And what we see is for sub-microns roughnesses, white light interferometry is still the main technique and sole technique to use, covering a large field of views. In that respect, focus variation will have a background noise which will be dependent on objective you use, in the same way as confocal, for instance. So here we were forced to use 20x objective to make sure that we get to around 0.8 or 0.5 microns roughness capabilities. Last but not the least, whenever the system is involved into QA, QC, it means it could be several systems checking different parts or different factory sites having the same process to control. In that case, the tool-to-tool matching is really critical. So what you see here is an example of R&R on the roughness comparators, where we measure the same locations within different system and different locations together with different operators. So we will really exhibit the variability due to the use, and get actually a dispersion below 2%, which is extremely good for tool-to-tool matching on the roughness measurements. So that being said, it's clear that the system has a good, robust quality for metrology. But what's about whenever we start to changing the system into a very high difference reflectivity sample? This is an optical technique, so we all know that at some points high difference of reflectivity may lead to some issues. So one of the tests which is done here is the USB memory stick, where we have a high bright reflective metallic case together with a carbon black polymers with low reflectivities. So whenever the system is on real-time measurements, you see that actually to get enough light and see details on this black case, the whole metallic frame is almost saturated in red. So the question is the system able to measure, and what kind of metrology and repeatability can we expect. And here you see the results. So in one single measurement, the system can automatically extract step height, roughness of the top metallic case and bottom black polymers. And you see after 30 measurements, plus minus 1 sigma deviation. So what we see all across the measurements, measured values, is a repeatability which is better than one person's on a range of tens of microns up to 500 microns. So over a wide range, the system is definitively highly robust versus such a saturations. It's also important to understand that here we did a single scan with single acquisitions, no need to do dual acquisition or to slow the scan speed to collect a frame at the different illuminations and intensity levels. The system is capable right away to measure. So it shows throughput as well in such challenging conditions. So that being said, I've shortly discussed about background noise, but I did not really come to the point of what kind of vertical resolution you can expect. As I say, vertical resolution depends on the objective. The higher the magnification is, the lower the resolution will be. The higher the resolution would be. So here this is an example with using a 10x objective on a printing light line over a metallic case. So you see there is a quite significant light difference as well between the dark line and the case, which is brighter. And what I want to point out here is the system has all analysis capabilities, such as automatically we can extract the step height in average and work out, for instance, the dispersions. If you don't have the right method to extract the height, which is around more standard methods, you may see a higher fluctuations, or you may not even see some measurements here. So what we see here with the right analysis method, we obtain a thickness which is around 13.7 microns plus minus 20 nanometers. So it shows here a vertical resolutions capabilities around tens of nanometers, which is still certainly a minimum 1 order magnitude higher than wide interferometry, but still very decent to go for precisions engineering part, for instance. So the summary of that is whenever we speak about using the best method between white light interferometry and focus variations can be set into this graph. On that graph you see also different technology plot like stylus profilers or atomic force microscopy. And what is displayed is the range of applicability of those different techniques, including white light interferometry and focus variation. So what we see is the horizontal axis is the lateral resolutions, which is in the log scale, and the vertical axis state the height again in logarithmic scale. So what we see is atomic force microscopy is made for super high lateral resolutions down to nanometers and sub-nanometer vertical resolutions, while the rest is nicely covered by focus variation and white light. And as we saw, white light interferometry will be more on a space of high lateral resolutions, high vertical resolutions, while focus variation will cover through the speed and illuminations larger field of views. But that being said, you still see the stylus cover and overlap very much all that range. And the reason for stylus to be still present is the fact that if you have thin optical transparent layers like below 100 nanometers, stylus is still the reference technique to measure topography and thickness of that thin films. To be more precise and oriented versus applications, you see the same time graph with only white light interferometry in blue and focus variation in purple. So what we can see is actually on application space, white line interferometry will be very much implemented for smooth surfaces, such as very polished, mirror polished surfaces, metallic or metals or optics. We also can extend the field of view very quickly in a range of a few minutes. We can measure flatness of like sealing surfaces, or especially in automotive worlds. Into MEMS and semiconductor, there is a need of very high precision step, making like measuring microns, tens of microns, with few tens of nanometers in a quick manner with a large field of view. So all that is very well addressed by wide interferometry instead. And for roughness, as we discussed, sub-microns roughnesses are very well measured and addressed by white light. We can use very low magnifications like 5x objective, and in almost one single image, 10 seconds, we get the right measurements. For focus variations, whenever it starts to be much rougher with larger field of view, which is required, then focus variations plays a role and overlap with white line interferometry to go up to very step surfaces like gears to measure gear tooth, or pin protrusions, or simply measuring fracture surfaces where you need to extend to square centimeter and have almost 10 millimeter range. So what we see is, in essence, to cover all applications, the two technologies nicely overlap and are complementary. So now it's time to illustrate the capabilities through real applications. There are several case studies here. The first one is about tribologies. So tribology means servicing lab performing tribal tests, or research about tribologies and wear time, but also failure analysis lab where the part has been broken and we want to understand the reason behind it. So one of the application is through Bruker portfolio. We have designed a module to test different materials for brake pads. So brake pads are under constraint to change materials due to regulations. So some of the component needs to be removed and replaced. However, the efficiency of the braking still needs to be kept. So the modules is aimed, tribology modules is aimed to test different materials and see the effectiveness of that. So what we see here is a brake pad button, which is a 13 millimeter diameters, which can be scanned into less than 9 minutes and gets a nice color image where we nicely see the presence of metals in some locations or some dark materials. So colors really definitively help to define where the components are, and we can just match the studies of how important the defects are on that metals compared to the rest of the surface. But also we can measure this brake pad button before and after the test. So what you see here in the red is protrusions, while after the test you see cavities and big cracks here in blue. So it assesses and it allows direct quantifications of roughness, initial roughness. This is important to understand the true contact areas because the spike will actually sustain the load, and it points out the need for certain run and in order to have the perfect contact and get the right information. But also after the test, we can also in the same way quantify all the cavities which are responsible, triggered by tearing and galling. So can have average diameters, volumes, and maximum depth of this one to really assess and quantify the wear and define whether it is appropriate or not. The second example is really more heavily damaged latch, and you see this is quite a large area of 9 millimeter by 18 millimeters with a scan range around 0.5 millimeters. And again, the speed of focus variation allow us the measurements in 8 minutes, which is fully acceptable, especially if you have like tens of the samples with different conditions to measure. And also color image here play a key role, because colors of, let's say, unchanged surface is different from the damaged surface, which is very dark. So the color masking can quickly isolate the surface and define only the bright area to be the reference one and define a perfect zeros. And by doing that, the analysis software, which is present by default, will automatically measure the pileup of matters as well as the missing matter. So you can really automatically calculate the missing volumes in order to assess the wear rate in a very accurate manner. So everything which deals with lifetime studies can quickly be done through our 3D optical measurements with focus variations. The other applications lies for corrosions, and corrosion is a big topic, for instance, in automotive, but even bigger when we think about the pipe and valve manufacturers for oil and gas. Same apply with all the coating research that aims to prevent corrosions. So to test actually corrosions, because corrosion is a very complex process, most of the time is better to use a sample called coupons, which is placed in the same conditions as the pipe, so either externally into corrosion chambers or standard corrosion protocol, or either directly inside the pipe itself, and those coupons are then removed and sampled and measured in a regular manner to study how healthy the pipe is. But this requires many measurements, and usually to measure corrosion effect, the coupons are measured in terms of weight. So there's a weight lost that will tell you how much corrosion has occurs. One of the point is when we look for the corrosion rate, which is the critical parameters to obtain, the weight loss is the first input. The second input is definitively to know the alloy densities. And in case of a single type of metal, such as aluminum, for instance, this is quite easy because it's homogeneous materials. But whenever it's in alloy, such as stainless steels and cornels, you may wonder what kind of density you have, especially if one of the chemical phase is let's say targeted by corrosions. So you may just over or underestimate corrosion rate bit by that way. So that's the reason why that in corrosions, usually coupons are measured by 3D optical profilers. Here this is a coupon of 23 by 47 millimeters, and with a range which is around 2 millimeters. So you see a very large volume. If we apply 2.5x objective in focus variations, it takes 7 minutes only to measure all that surface. And while with white line interferometry, same sample will certainly go for 1 hour. So there is like a time element and throughput element which is critical. And then from automatic analysis, we can work out the total volumes of all those cavities, which is around 0.018 cubic centimeters. We can automatically get out the deepest point, which is 0.4 millimeters, as well as the largest diameters. So all the critical elements will be sorted out after 7 minutes, basically. So the total loss volume will be put into this formula to get the corrosion rate, and also you will estimate how severe the corrosion is. Effectively, it's the deepest point and largest diameter. You will see whether you have a dangerous or hazardous corrosion pits which is created, and that just could create a full crack or a full hole through the coupon. So now I will go for the third application, which concern aesthetic and perceptions. So we all know that whenever we enter to a car, the interiors will look like either shiny, matte, comfortable, aggressive. Same happens for all the fabrics, tissues, or even the paper whenever you take pen and start to write on it. So this is what I want and show here is how focus variation plays a role. For perception into, let's say, a car dashboard, for instance, it is understood that we can, through 3D measurements, correlate how shiny or matte a surface is just by looking on how the groove of that laser-like plastic are made and the roughness on the top, for instance. But this required to cover a large enough surface, which is here around 8 by 8 millimeters. We could easily extend that to much larger and then put that type of surfaces into either modeling that will tell how the surface look like. So instead of printing the full board, we will just measure a small coupons and replicate that into software to get first impressions. Either we can measure, let's say, a nice and good dashboard versus a bad dashboard to understand where the issues lie. So what you will see here is an angular power spectrum density that tells you that you have main directions along that diagonals, but also you see you have a little protrusions along another directions, another one as well here. Which tells you that certainly this is not what the designer wanted. It was more like two main directions without this peak. Also, through the ISO 25178 norm, there are normative texture parameters that will help you to quantify all this. So instead of having an impression on an image, you can go down to a quantified value, which is easier to get a feedback regarding production. So for instance, the STD and STD minor will show the main stroke directions, plus 46 degrees here, minus 55 degrees here, and it will tell you what kind of aspect you have in between the peaks. You can also, usually this is the case in terms of matte and shiny surfaces, you will use the mean slope roughness, so the SDQ, that tells that we have a mean change of slope around 8.5 degrees. So the higher the slopes are, the more specular the surface is, and the more matte the surface is instead of being shiny. You can also use the SDR, which is the develop areas. So instead of having a perfectly flat surface, you develop a certain areas, which certainly help to understand, for instance, how much the surface will capture dust and how dirty it could become. The other one, which is pretty illustrative, is really getting impression of papers. So we know that taking a ball pen and writing on different type of paper, you get different perceptions, and for same paper with different pen, you may have again different perceptions. So here what you see is a nice 3D image that shows a trace made by a pen, and the color image together with topography leave you all the informations. So when we write with a ball pen, we actually leave a groove into the paper, and this groove is around here in the range of 61 microns, which depends on the ball radius. But also what you see with the color image is exactly where the ball ink has been deposited together with coloration of paper fibers. Here in that case, we nicely see that the ink was really nice imprinted along different fibers in there, and we saw that the fibers start to be well arranged versus a more random arrangement around this white paper. So the correlation between color imprint and groove leave you a complete set of conclusions. And here you have a good illustration of 3 different pens on the same paper, and what you see here is a direct analysis. So You see the color image that shows exactly where ink was set, and the white boundaries tells you exactly where the groove is. So if we go to this pen, which is pretty high quality, you see that the inks more or less follows the grooves with certain variations. For non-working red pen, you see that actually we have patches of ink, but we still leave the groove around. And finally, for normal blue pen, you see that actually there is like much more variability in terms of grooves. Sometimes the ink is not deposited along a line, and this ink actually diffuse a bit more, which has to do with the viscosity of that ink and how it's diffused through the paper fibers. So in that essence here, the focus variations helps you to really see and combine color image together with topography to tell you the whole story behind how the writing process occurs. And I'd like to finish with the new manufacturing techniques. So there are very hot topics regarding additive manufacturing and 3D printing. So here, focus variations will help to fine-tune the manufacturing process or to help the qualification of printer, porter selections, as well to ensure quality control. So when we speak about additive manufacturing, is actually we like to build a part layer by layers instead of turning a wall block. We simply start with a bed of particle, which can be metal particle in that case, and we'll use here in that process of laser selective melting a laser that melts these porters into a weld metal layers. So this is like an example of good process. There are several issues that can happen, and there are several setup to take into account. As first of all, there are a lot of variability due to the porter size, due to the porter chemistry as well, like oxygen, hydrogen contain or sulfur. All that can be analyzed with different Bruker divisions with analytical and chemical system. But once you're set, we can understand that if the layer is too thick or the laser power too weak, the weld metal will not reach the bottom, and then you will have a non-cohesive volumes. So we are losing mechanical properties and losing here the part. The same way, if the laser pour is too high, you may just melt and previously met surfaces and create pores. Pores will be very much spot out by micro CD, for instance, with X-rays. And in that case, optical profilers would not be a good method. But then, if you move the laser too fast, actually you create some voids. So when we look to good process or some kind of bad processes, optical profilers can look to it and how the process went, either looking from the top, like with the voids here is, either looking from the side and looking to the layer to layer homogeneity. So this is an example of a complex part built in through additive manufacturing. This is made of aluminium porters, and what you see is a large field of view of 18 millimeters by 6 millimeters, and you see the sections where you see in blue the wall shape, and this is one-to-one aspect. So what we can determine here is we have 45-degree slopes, and along this core parts of low structures, we go very deep with very steady slope, and this is where focus variation help to measure the wall shape. So we can deduce here the curvature, which is around 10 millimeter radius. We can extract as well the waviness in green, as well as the roughness in a red. So all that in the one single measurement, we can just get and create this information. So this will comply to GDT and see whether the radius and the roughness are within the specifications or not. So it's more quality control here. But in terms of fine-tuning the process, by using a 20x objective, we can nicely see the microstructure, and this see, for instance, two different powder like Inconel and aluminum being used with the same laser parameters and scan speed. So what we see is the wall microstructure is definitively different. Colors allow us also to spot out what could be a potential defect here or pores. It's also tell us in that respect that when we measure micro roughness for that process, we don't see very much differences in the mean roughness. So we have 22 microns here for aluminum, and we have 24 for Inconel. Why visually we see a huge difference. And this is here again where the new normative S roughness parameters that will help us to convey back to parameters. And parameters, quantified parameters, is much easier to use in order to feed back into the process. So what we see here is the aluminum top view and Inconel. So now we see that we have partially non-melt particles. We form blobs, so maybe not the perfect processes. And here we nicely see for Inconel a nice front, melt front being moved around. Few amount of unmelt or large particles being there. And to quantify that, we can actually use the parameters which are like the invert of radius of curvature. So you have a very curved round particles, this number will really change. So short radius will imply a couple, and here you see a different radius as well of curvature. So you see a big change of 60% in terms of invert radius of curvature, stating how the surface is more like ripples rather than round shape. The same apply in terms of SDR. So it tells how much developed errors we have, and whether we'll have an issue further in terms of painting, for instance, having ability for the paint to anchor or not on that surface. So all that will couple back to fine-tuning the parameters, and also further understanding whether the surface needs further, like sandblasting, further processing, in order to comply with the use or the next process steps, such as painting coatings. Now I will finish with the 3D printing of PEEK materials. So 3D printing is another way of building a part. So a wire, PEEK wire, is melted and extruded through a printing head, and the system just moving XY to print layer to layer and form the whole object. So if we look to the side of that object, we'll see actually those layers. And the whole challenge with PEEK, it's a very challenging materials to fine-tune the printing parameters. So you need the proper temperature of melting, you need the proper speed, extrusions, pressure to make it effective. The point is, what you see here on the left and the right is a good process because the part has been found to be appropriate, and this part here has been found bad. if you look to a point of view of visual aspect, you see a differences. Somehow the layer here seems to be irregular, and it sounds like to have some kind of merging. The mean roughness also is very different, but the mean roughness does not tell you something which is directly linked to the process. So here the key element is having the mean correlation length that works out automatically the spacing of this line. So it brings a value of 77 microns, which is really what is expected for the process of the layer thickness. And here you see 88, which shows that there is a partial fusion. So basically the peak materials is extruded too hot and start to melt further down and create issues on that surface. So in that case, having and scoping with very rough surfaces, focus variation can extract directly parameters which is linked with the process. So you can define an experimental plan and find the best parameters through iterations and getting this mean correlation length plot. To conclude, as you have seen, the 3D optical profiler based on focus variation indeed expand the capabilities toward rough surfaces and large field of view. The reason being that the system is able to have a very fast scanning speed together with the proper lighting, and that the principle of measurements for the focal plane is based on contrast method instead of a pure intensity methods like confocal white line interferometries. But all that combined with large Z range and wide field of views actually allows higher throughput and enable new applications such as like corrosion measurements, fractured or tribology surfaces measurements. What is important is, even so it's going to larger field of views and a larger Z range, this is still a high-end metrology equipment having tens of nanometer vertical resolutions and being robust versus different situations such as very high contrast difference with spot. The more important is, as per a user, this 3D optical profiler based on focus variations allows direct quantifications of the roughness, and through the new S parameters, which are from the norm, ISO norm, we can directly link the roughness with the surface functionalities, as we have seen with the different examples. I'd like to thank you for your attentions. If you liked any further information, feel free to contact me at samuel.lesko@bruker.com. Now it's time to answer the questions and get this thing. So the first questions is about whether we could integrate both the white line interferometry and the focus variation techniques on the same platform. So besides the fact that it is potentially possible, we prefer to have two different platforms, such as we have the proper optical paths optimized for the measurements. As we understood, focus variation is all about getting a color image, getting also ring lightnings, which is very different from white line interferometry, where you want a more well-shaped coaxial light, getting a camera which is usually black and white to ensure the high signals to noise ratio. So in that essence, this technique are complementary, but it's very challenging to keep up the performances on the top for both technologies whenever we merge that on the same platform. The second question is saying that For instance, we have a question regarding how much lower roughness we can measure. It's clear that what has been shown is using a 20x objectives, and 20x objectives allows to measure something like 400 by 400 microns space, which is good enough to have a certain assessment for the roughness. But in that case, we need to stitch together in order to go for, let's say, a minimum 0.8 millimeters or 2.5 millimeters. So which render the focus variations slightly challenging in terms of measuring roughness of submicrons. With white line interferometry, we will use a 5x objectives. We will cover something like almost 2 by 1.5 millimeters in one single frame and get nanometer resolution. So it's much more effective in terms of throughput to choose white light. We could potentially go with much lower roughness values, going to 50x or 100x objective, but this will shrink so much the field of view that, again, focus variation will not be applicable in the sense of it will take an hour to get the right area scan, while it will take a few minutes for white light. So it's all a question and balance of what we can grab in terms of best technologies. In that instance, again, focus variation should be used for what it is good for, and likewise, the white line interferometry should be used for what it is good for. So white line interferometry has unique capabilities to measure large field of view with as even sub-nanometer vertical resolution, and that's a unique strength, in the same way that focus variation is able to measure raw samples. There was a question regarding what is the largest steep slope limits focus variation with the biggest. So there's a question regarding the maximum angle we could measure. So usually for optical profilers, the limits is really depending on the technique, first of all, and secondly, depending on the objectives. If you think, well, a 90-degree slope will require very high lateral resolutions, and usually in optics we are limited to maximum 0.5 microns lateral resolution, which will allow us certainly to measure slope around 80 or 85 degrees with a certain accuracies. So that's where we stand. For very steady slope, like in semiconductors, we prefer to use atomic force microscopy, which will give here resolution around the 90-degree slope. And then there will be another question regarding roughnesses in terms of the differences between the focus variations and white line interferometry. In terms of roughness, we all know that every system will have their own imprint and transfer functions. So in essence, with white line interferometry, we use, as I said, a 5x to measure such a roughness, which has a different optical function than the 20x objectives. So in that respect, it is not fully identical, and we expect discrepancies between them. That being said, the agreement between so much different technologies on optics is already pretty good in that sense. So, and there is also a question regarding Alicona. So you may know that there was an announcement today about Bruker signing up an agreement to purchase Alicona shares. Indeed, we are pretty excited to welcome Alicona into our divisions. And it shows that clearly we are pretty serious in focus variations. So thanks. I see no more question being ask. So as I said, whenever you want to reach me out, samuel.lesko@bruker.com. If you like to get the slide and the recording, the whole webinar is being recorded and will be displayed into our Bruker website on the webinar page. So you simply Google Bruker webinar profilers and you will go straight there. Thanks for your attentions, and wish you either a good day for people in the US, either a good evening for Europe. Thanks a lot. Goodbye.